So far we have discussed theories where fermions and vector bosons are involved. In general, we can have Feynman diagrams where the particles in the loop can be a scalar, the external lines can be scalar, the particles in the loop can be spinor particles, and the external lines can be vector, and so on and so forth. You can have a tensorial interaction also, and the result of these interactions is generation of or the types of vertices, those are generated here. Generally, for a scalar interaction, the coupling constant is g, which is a scalar. For a spinor and vector particle, the vertex is given by the coupling constant times a gamma matrix, gamma mu, and it can become complicated as the type of the interaction becomes more complicated. So, the final observation of this analysis is when you try to build up the structure of such diagrams, the first diagram being a scalar, we can say that okay, it is a scalar which is some function of the momentums, and this function of the momentums should be Lorentz scalar. In the second case, we have two vector like vertices. So, this amplitude must be having a index, and these indices are given by mu and nu, and this tensorial object in principle or has to be built up from the using the variables, those are there in the theory, those are going. One of them is k mu, that is a 4 vector. The other one is the metric tensor of the underlying space time metric g mu nu, that it can be, and the third one can be epsilon of mu nu lambda rho, is a completely antisymmetric in any two indice exchange Levy-Civita symbol. So, these are the ones those can contribute. Additionally, if we have a external electric field or magnetic field, then we can also have something like f bar of ij or mu nu that can appear in the description of 2-point function, and if they can appear in the description of the 2-point function, then they might as well appear in the description of n-point function when the indices are suitably adjusted. So, if someone is going to make the tensorial structure of this 2-point function mu nu out of these variables that you have drawn on the right side, one has to really make sure that these objects, those appear in its description, respect the symmetries of the theory that we have just discussed. And as a result, you can write this mu nu index objects as some scalar function, let us say f L of k times a of mu nu plus g L of k times b times mu nu plus c L of k times c of mu nu so on and so forth. However, the issue that is important over here is this writing in terms of the tensors a, b, c cannot keep on going ad infinitum. it has to terminate at a point, and it should terminate at that point when the new additional tensors are no more independent of each other. So, here we can stop to say that this construction of these 2-point functions, so far as the vacuum theory is concerned, a vacuum theory can have an axial symmetry or broken axial symmetry. That is what gives rise to epsilon, mu, nu, lambda, rho, etc., etc. And with these we can make these new tensors in terms of those and the new scalar factors. We can write down the full amplitude or 2-point amplitude as a sum of these little pieces. And these little pieces, a mu nu, b mu nu, c mu nu, etc., and g, f and small c should be subjected to the symmetries of the theory that is under consideration as far as vacuum theory is concerned. So, having cleared up this particular aspect about vacuum theory, we should make our move next to theories. Those are considered in a medium. So, does medium introduce any new vectors to construct the amplitudes or not? If it does not, then ideally there would be no structural difference between the theory in vacuum and the theory in a medium. It will be identical except for kinematical factors and statistical distributions. But if it is not, then we ought to see what modifications or new interactions or new type of structures that they can introduce. So, to appreciate that, we need to understand the structure that is usually called as propagator, and what it means is, by the name propagator, it carries the excitation of a particular quanta from one particular point in space time to another particular point in space time. That is the name. For fermions, this 2-point, it is not a 2-point, it is a propagator that is usually given by the argument of the momentum that it carries by I times p slash upon p square minus m square plus I epsilon minus 2 pi into delta of p square minus m square into something called eta f of p. In reality, this is not p, it is the 0th component of p or the energy component of the momentum that contributes. Now, what is the difference between these two factors? Those have appeared here with a negative sign between them. The first factor carries no information about whatsoever about temperature, chemical potential or anything. However, the second factor we can see has a multiplicative term eta of p naught, and this eta of p naught, when it is written explicitly then throws up the corrections those have dependence on chemical potential mu and temperature when 1 over beta is equal to temperature in units where K Boltzmann is equal to 1, and in addition we have H cross is equal to C equal to 1. So, the medium effects finally show up in the second factor. Not just that, it also has thrown up another issue, which is the appearance of a constraint delta of p square minus m square, which tells you or tells us that the particle is always moving on shell. The famous energy momentum relation E square minus p square c square equal to m square c to the power 4 turns out to be equal to p square equal to m square, or p square minus m square equal to 0 if we identify E to be the 0th component of the momentum 4 vector and we take C to be equal to 1. That means this energy momentum conservation is obeyed by the second piece. So, in a medium, technically it is spelled like this: in a medium, the particles move on its mass shell. So, it just moves as if it is a real particle. That is where the delta function comes. And the factors of 2 pi basically appears to construct a delta function out of the 2 vacuum propagators. So, that is what it is. And now you see, instead of writing P naught everywhere, if you replace P naught by P dot u such that u vector has only non-zero momentum in its 0th component, then you can write this statistical factor n or eta f of P not as P dot u theta of P dot u by e to the power beta of P dot u minus mu plus 1 plus theta of P dot u minus sine e to the power minus beta P dot u minus mu plus 1. Not just that, you can now define a charge conjugation operation which takes your particles to antiparticles, mu going to minus mu, and to keep the structure of the statistical factors same, you also must have u mu going to minus of u mu. So, simultaneous change of these two should give you a neutral effect on the distribution function or the statistical factor, and you realize that apart from the vectors that we had just defined a while ago in terms of k, g and epsilon, we have another additional vector that can crop up to extend the paradigm of our system, that is u mu, that is the 4 velocity of the medium. So, under charge conjugation, not just a mu's would go to minus a mu, we have u mu's going to minus u mu, and chemical potential should go to minus of chemical potential. So, this completes the description of CPT carrying factors in a Feynman diagram. And for a system that is at rest, we have E mu is equal to 1, 0, 0, 0. And for a system that is moving with finite velocity, these elements can be different. Thank you.